We're going to take a look at the area formula for regular polygons and how they're related to the array notion of multiplication and how we can relate them back to a triangle and rigid transformations, in this case, reflection. We're going to start with the pentagon. We can estimate the area of this pentagon. It has a width of about 4.5. It has a height of about 4.5. So, the area is going to be around 16 units. But that isn't an exact area. It's really just an area taken from kind of constructing a rectangle around the figure, one that maybe looks something like this, and then kind of estimating a little on the low side because we know we're going to be taking away these spaces, these triangular spaces on the outside. So maybe the area for this thing is around 16, something like that. But there certainly is a formula for finding the exact area. So let's try to find the triangles that live within this pentagon, this regular pentagon, regular because all sides are the same length and all interior angles are the same measure. So let's see how we can find the center. Here's my midpoint tool. It tells me to select 2 points, a segment, a circle, or another conic figure. Well, I don't want the center of a segment, and I don't have a circle or conic here. I've got a pentagon. But what's great about the regular figures is that around each of them, I want to make a circle through 2 points. Okay, 3 points. Is that around each of them is a circle that touches all of its vertices. And that allows us to do quite a bit of measurement. And it also allows me to get a center point for this circle. So there it is. I'm going to move my little label out of the way. And I'm going to use that center to construct a triangle. And I'm going to go ahead and turn this circle off. And I'm going to go to Options and turn off labeling. And let's prove that we have a triangle that can be reflected over a line. How many times? Ooh, I just reflected my polygon, which is not what I meant to do. Where's my triangle? Let's take this tool, reflect my triangle over this line. I did it again. This tool, reflect the triangle over this segment. There we go. And let's take this tool and reflect this polygon over this segment. Tool, polygon, segment. How many times? 1, 2, 3, one more. Tool, polygon, segment. And I should be creating a copy of the original pentagon with no overlap. So I can turn off the original polygon that we created. And can I play around with any of these points? Not sure. Yeah, I can. I can turn off the original polygon we created, and now I've got this figure that was created completely independently. I'd simply use the midpoint of the circle that surrounded that pentagon that I made, and I attached triangles to it. So we really could start with a regular polygon on 9. Now we can make the hexagon. What the heck? We like hexagons a lot. So let's make it, though, out of a regular triangle. So if we choose the measure of the central angle carefully, in this case we know we have a 60-degree angle at this vertex, then we can construct any figure any regular figure we want. Now we could easily find the area for this particular triangle. We know how to find areas of triangles by replacing that with a segment. How about if I had a point on the horizontal axis here, and I'm going to replace that with a segment, and I'm going to turn that off. And I'm going to replace this with a segment. If I knew the length of this height and the length of this segment, I could get the area through an easy formula for this triangle. So let's see what segment that is. This is segment N. Segment N has value 2.17. And this segment that we created here, segment P, has a value of 2.5. So we could use these two figures. Where's my snipping tool? I've pushed the wrong button. So we have those two values. We multiply them together. We take half. So go ahead and do that. Find me the area for this single triangle that has base length 2.5 and height length 2.17. Get your calculator out and go ahead and we'll enter the area into this text box. And we'll fix the spelling. 2.5 times 2.17, result divided by 2 gives you an area of 2.7125 square units for this figure. Now, we're now going to create the hexagon from the equilateral triangle we started with. There's going to be 6 of them. The area is going to be somewhere between 12 and 18 because we're simply going to multiply the area times 2.7125. So let's reflect about a line this figure over this line. Let's reflect about a line this figure over this segment. Why doesn't it like me? This polygon over this segment. Well, let's go this way then. Sometimes it doesn't consider the segments of the new polygon to actually be segments. Sometimes it's because too many things are highlighted over here. So let's highlight polygon 4 over this side. Didn't work. Let's highlight polygon 4 prime over this side. Still didn't work. Okay. So I want to do this without overlap. So let's see if it will let me put an intersection point here. Didn't get an intersection point, so I'm just going to have to carefully as I can place a point here and place a point here. My other option is to use the original triangle, this guy. Let's reflect it through the point at its vertex. This guy through here. And what if I were to rotate then and I wanted it to land here? Is that a rotation of 120 degrees? Let's try it. Rotate around this point, this figure around this point, 120 degrees. I almost don't care if it's clockwise or counterclockwise because I need it both. So now let's do that again. This figure over this point. Rotate around a point. This polygon, this point, 120 degrees, and go the other direction. Okay, so does this convince you that 6 triangles with area 2.7125 represents the area for this hexagon? Let's make the hexagon created by these 2 points that has 6 sides. And let's find the area of it. We're looking for something that's around 16.27. And is this Polygon 5? Polygon 5 is pentagon JK. So this height right here of the original triangle that lives within the pentagon, or the hexagon, is a really important measurement. It'll get me the area of the isosceles triangle using this one side length, and multiplication will get me the area of the whole figure. Your task will be to define the parts that are used in the area figure formula, the area formula for a regular pentagon. So you will discuss the parts of the area formula for and this is the generalized area formula for a regular pentagon, and you will say how they relate to the area of a triangle, which relates to the area of a rectangle. You'll have access to this file. Oh, I just changed something I didn't mean to change. You'll have access to this file so you can play around with making another figure. So you're working on developing an understanding of how these area formulas are all related, which is just a little bit stronger, actually significantly stronger, than developing a knowledge of the area formulas. Understanding stronger than knowledge.